So hello students, today we are going to look at a physics problem from the textbook of Irodov on electromagnetism, and namely this is motion of charged particle in electric and magnetic field. So many students have requested me that they have not been able to solve this question, or even the solution for this question which is there on the internet is something which is beyond their scope, namely the maths which has been used. So what I've tried to do over here is use simple maths using complex number so that everyone can understand. So let's look at this question. Okay, so this is question 3.395 from Irodov. So it says a charged particle is of mass m and charge q is released at the origin. So over here, okay, so you have a charged particle q and it is released at origin from rest, and there is an electric field and a magnetic field. Okay, but namely the electric field is variable, so it is given your electric field is your em cos omega t. Okay, so this is a time varying magnetic electric field, and the magnetic field is constant. So now if you look, there is another question here where the electric field and the magnetic field are constant. So that is very easy, which anyone can solve. But this is where you have a time varying magnetic electric field. So therefore, we'll just see how to solve this question. Okay, so the first thing first. So in this question, we know that the electric field, electric force will be in the x direction, Fe. Okay, and the magnetic force. So magnetic force is always perpendicular to the plane of the velocity and the magnetic field. So the velocity is in the y direction and the magnetic field is in the z direction. So V cross B. So it will be in the positive I direction. So this is your magnetic force. Right, so you have the electric force in the positive y direction, you have a magnetic force in the positive x direction. So therefore, we know for sure that your velocity will only be in the x and y direction. Okay, so the particle is not going to move in the z plane. So therefore, we start with the first part, which is your velocity is vxi plus vyj. Okay, so that is what you need to understand first. The motion of the charged particle is going to remain in the x and y plane. Fine, then we go to the Lorentz equation. So this is your Lorentz equation. So this gives you the force on a charged particle which is moving in a magnetic field and of course in an electric field. So E plus V cross B and the whole multiplied by Q. Now we put the value of the electric field. So your electric field is Em cos omega t j cap plus your Vxi plus Vyj, which is what we have for velocity, into Bk cap. Why? Because the magnetic field is in the positive k cap direction, right? Now we further simplify this. So you get a I cross k. This is I cross k, which is your minus j, and you got a j cross k, which is your positive I. Okay, and then you multiply this. Next, we are going to put the force as this is mass times acceleration. This is mass times acceleration. But again, you need to understand, since the force is in the x direction, x and y plane, so therefore the acceleration will also be in the x and y plane. So only we'll have two components. So you have a ax I cap and a ay j cap. Okay, so we equate it with the terms which are there on the right hand side, and then we club together the I cap terms and the j cap terms. Okay, once we have done that, we get the acceleration in the x direction. So this is the acceleration in the x direction, which we can also write it as dvx by dt. Remember that. And if you compare the I cap coefficients, then your ax will be qb by m into vy, and your ay, which if you compare with the j components. Okay, so we have a ay which is also dvy by dt. Okay, so if you look at the terms on the right hand side, it is q by em cos omega t minus q by m into vx. Okay, so remember, these are my equation number 1. Okay, and these are my equation number 2. So which we are going to use it further to solve this thing. Okay, now comes the most important thing. So as I said, I'm going to use simple complex number. Okay, not use some very difficult method to solve this equations. So we just take a function v. Now this is not velocity, this is a function v. So this is a complex function. So it has a real part which is vx and a complex part which is I times vy. Okay, and we know at t is equal to 0, that is initially the particle is at origin and it is released at rest, so therefore your Vx will be equal to 0, your Vy is equal to 0, so therefore the complex function V will also be 0, right? Then we go further. So you take a derivative, okay? You take a derivative over here. So we have taken a derivative. So dv by dt is dvx by dt plus I times dvy by dt. You can either take a screenshot of this, or don't worry, I put the PDF of this entire solution in the description box. Okay, so you can download that or you can take screenshot. So suit yourself. Right. So now we have. So now we put back equation 1 and 2, which we had defined over here. So which was your dvx by dt is qb vy by m, and your dvy by dt is this big function here. So we put it back over here. So this is where we do the substitution. Okay, now we club the real parts and the complex part. So I'm sure you are well versed with your complex numbers, right? And then what we are trying to do over here is try to simplify this further by using the Euler's equation. Now what is the Euler's equation? You all studied complex number. So your Euler's number is e raised to theta is equal to cos theta plus I sin theta, e raised to I theta. Okay, so here you have a e raised to I omega t, which is cos omega t plus I sin omega t, and e raised to minus I omega t is cos omega t minus I omega t. So simply put, your cos omega t will be your e raised to I omega t minus e raised to minus I omega t divided by 2. Okay, so you put it back over there, and now what we do is we multiply the LHS and the RHS by e raised to I omega t. Why? Because we want to simplify it further. Okay, so there are various ways of doing it. This is one of the way. If you have a better way, be my guest. Okay, so we multiply the first term by e raised to I omega t, and what we have done is so there is a term over here, okay, which is of that e raised to I omega t. So that we have, brought it on the other side, right? So we are just trying to club terms, and whatever is left on the LHS remains over here, right? So just go through it. You'll find it very simple. But what is e raised to I omega t dv by dt plus I times omega e raised to I omega t v? This is nothing but the derivative of v I omega t. Okay, you can do so this is the taking derivative of u into v. So we come to here, and now what we do is we integrate on both the sides. So we integrate on both the sides. So we get a e raised vi omega t, and that is equal to this. So you get basically two terms. Okay, one is your e raised to 2i omega t and integral of dt. Okay, so which you can do it very simply, and we get this. Okay, now don't forget to put the constant of integration, right? So since we are not taken definite integrals over here, is better you put the constant of integration, and to evaluate the constant of integration we use boundary conditions. Now what are the boundary conditions? Is the initial condition. Okay, so these are also called as the boundary condition. So at t is equal to 0, we have v is equal to 0. So put it back over there and find out c. So we get c is equal to e raised to, so negative em by 4b. So put it back. Okay, and then club like whichever term you can club. So you have a em by 4b common. So we take it over here, and then finally what we do over here, see there is a e raised to I omega t. So you multiply the entire term. So we are going to multiply, we're going to remove this, so multiply by e raised to minus I omega t on LHS and RHS, right? Okay, so then we have removed that e raised to I omega t from the LHS, and this is what we get, right? Then you combine whatever you can, and here we again get e raised to I omega t minus e raised to minus I omega t. So which, using the Euler's equation, we can put it as 2i sin omega t, and the balance term are as it is. The only thing what we have done again is write use the Euler equation and write e raised to minus I omega t as cos omega t minus I sin omega t, right? And then you go down further. So what we are trying to do over here is, again, we are trying to segregate it into the real part and the complex part. So then straight away we can equate. So after doing all these steps, we come to the real part, which is Em by 2b omega t sine omega t, and here this is a complex part. Okay, now remember my original equation, which was we have defined this complex function, which is Vxi plus I times Vy, right? Now compare this and this equation. So this is also V, right? So from by comparing the coefficients, we get Vx. So this is the velocity in the x direction. Okay, so component of velocity in x direction. So component of velocity in the x direction is Em by 2b. So it's a time function omega t into sine omega t, and the velocity in the y direction is likewise Em by 2b sine omega t plus Em by 2b omega t cos omega t. Okay, so once we get the velocity in the x direction and the velocity in the y direction, now we can find out the x coordinate as a function of time and the y coordinate as a function of time. So once you get that, then we can track the trajectory of the particle. Okay, so you have a dx by dt. Vx is nothing but dx by dt. Okay, so which you know, and then we integrate on both the sides. So this is a simple UV thing. So you can do integration by parts. Okay, so that is exactly what I have done. You cancel whatever you can cancel, simplify, and we get the answer. Okay, so this is your x coordinate as a function of time. Remember, we don't have to put the constant of integration over here. Why? Because at t is equal to 0, your x is also equal to 0. So your c is also going to be 0. So I have omitted that step because it's self-explanatory, and you get a dy by dt is so and so, and again you do the integration to get the y coordinate as a function of time, and finally we get this as the y coordinate as a function of time. So we got your x coordinate as a function of time. So this is your x coordinate as a function of time, and you got a y coordinate as a function of time. So this is your x coordinate as a function of time. Okay, so if you see this, so this is nothing but a trajectory of a spiral. Okay, outward spiral, right? So you are not going to get a cycloid. See, if E is constant and B is constant, then you are going to get a cycloid. But if E is a time varying electric field and B is constant, then this is the trajectory which we are going to get. So I'll just draw it for your reference. So the particle starts over here. So this is your charge Q. Okay, so this is originally at rest, and you have a Em cos omega t, and this is constant B. Okay, so what your x and y coordinate show you is that you are getting a outward spiral. So this is how it looks. So this is how it will go. So this is the outward spiral. So remember, this is in the x and y plane. Huh? So the motion is only in the x and y plane, and it will be moving outward. I hope you have understood the solution for this complicated question. And if you have any other question, please feel free to write to me. Thank you.